For our very first lecture today, we are going to I'm going to give you a gentle introduction into quantum mechanics. Okay, so quantum mechanics is, of course, arguably the biggest scientific revolution in the 20th century, with impacts on the lives of people. Okay, now of course there were many scientific discoveries in the 20th century, right? Things like relativity and so on and so forth. But arguably, quantum mechanics is the thing that actually affects your everyday lives the most. Okay, so the discovery of quantum mechanics actually took place over the course of a few decades or so. There's actually this very nice book that I read called 30 Years That Shook Physics. It's by George Gamow, a very famous physicist, and it's actually a very interesting read, and it's a very short book. So if you are interested, you can actually read it. This is actually a brief historic timeline of how quantum mechanics came about, right? So in 1900, Max Planck actually first observed, made a proposal that radiation is actually quantized. Okay, in other words, instead of thinking of things like light as a wave, you can think of light as packets of energy. And using that, he actually proposed that that quantization of radiation actually can explain certain observations that have been puzzling physicists for before, which is, for example, the black body radiation. Okay. Now, in 1905, then Albert Einstein himself then proposed that light quanta actually behaves like a particle. He used that to, of course, describe the photoelectric effect. Then, followed by that, then various scientists then began to apply that concept to other properties. So things like Bohr created a quantum mechanical model of the atomic structure. De Broglie then, of course, proposed the very famous wave-particle duality. And after that, you then have your Pauli, who formulated the exclusion principle, and showing that, of course, developed the wave mechanic equation. Okay, so of course, there are a lot of things that happen after these 30 years, but by and large, this 30 years actually set the foundation of quantum mechanics. Okay. Now, when we talk about first principles computational materials design, what we mean is basically that we are going to start from the equations of quantum mechanics, which is the Schrödinger equation that you see right here. Okay, and what you then do is that you then put in with some approximation. So we are going to go through the various ways of approximating solutions to the quantum mechanical equations, and you then plug it into a computer, and what comes out at the other end of your computer is some material properties, okay, after you do some analysis, right? Now, why are we interested in first principles computational materials design? Okay, there are two very important reasons. The first important reason is because we start from first principles, okay? This is why we call it ab initio techniques. Because we start from the equations of quantum mechanics, this is an equation that applies generally, okay? It applies universally across the periodic table. It is unlike, say, an empirical potential where if you fit it to one system, you can only use it for that one system, okay? You can't use it to, say, model another structure or another chemistry. Quantum mechanics is different in that sense. That equation is universally applicable, so you can use it to explore the entire periodic table. Okay. Now, the other reason, of course, is that because you are using computers to solve the equations of quantum mechanics, computers are inherently scalable, right? If you have double the computing power, you can double the number of calculations, or you can try to simulate a bigger bigger structure. Okay. So, in other words, this virtual laboratory is one that actually automatically gets upgraded every 18 months or so. Okay, you actually have, based on Moore's law, you have a doubling of computing power every 18 months, and essentially the size and the number of materials that you can simulate approximately in any given time also doubles every 18 months or so. Okay. So today now we have figured out how to compute many different properties with quantum mechanics calculations. Okay, so these are just some examples of things that I'm personally interested in. So things like what is the voltage of a lithium-ion battery, right? So as you can imagine, that's a very critical property if you are interested in designing a new lithium-ion battery material. Okay, and this is a property that today you can actually predict to within a 0.5 eV or so error. Okay, so in other words, before we even ask an experimentalist to go into the lab to try to make the material, we can already tell the person roughly what the voltage is, okay, to a good degree of accuracy. Now, the other property that we can predict are things like diffusivity or barriers to diffusion. Now, the example I show here is for a lithium-ion battery material, but of course this is a property that is universally useful across a very broad range of applications, right? So you can imagine if you are working with a solar cell, you want to understand how diffusion actually affects the stability of the material. You can calculate the diffusivity of the anions. You can also, of course, to get the diffusivity of lithium ions in the lithium-ion battery material and many other different types of applications. Now, if you are doing materials design, one of the main properties that you are always interested in is the phase stability of the material. So you want to know, can this material be made in the lab? Is this structure even stable, right? And again, this is something that today we actually can make a prediction of how likely the material can be made, okay? We do this by using the energies that we get from our calculations to construct first phase diagrams, okay? And by constructing phase diagrams, we can guess at how stable, how likely you can make the material, right? Now, it is not a foolproof prediction today, but you actually have a good guess, right? If a material is really unstable, then you wouldn't ask your experimental colleagues to go and try to make it, okay? There are also things like crystal structure. You can also get try to predict what are the likely crystal structures for a given composition or collection of elements. As I showed you earlier, you can also calculate things like the surface energies and surface energetics of the material, okay? Now, of course, the ab initio calculations have taken off a lot in the recent years, okay, in the recent past 2 decades. So as you can see, in 1990, the number of papers having things like the word DFT or ab initio in the title is less than, say, is probably a few hundred in that year. Today, we are really talking about tens of thousands of papers every year with some ab initio or DFT calculations in it. Okay, and here I'm really focusing mainly on just the condensed matter side. Okay, computational chemistry itself is another big collection of papers. Okay, and it has become so universal that it is very rare that you actually can find pure experimental papers without any computation in it. Okay, it is actually quite common nowadays that some of the experimentalist group, they will, in order to help support some of the experimental observations that they make, they will actually also do some calculations to actually verify that what they experimentally observe is also sensible. Okay. Okay. So as I mentioned, for quantum mechanical modeling, you start from the Schrödinger equation. So the Schrödinger equation is shown right here. Okay. So there's actually this very famous quote by Paul Dirac, okay, in 1929. He basically said that the underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are thus completely known, okay? And the difficulty is only that the exact application of these laws leads to equations much too complicated to be soluble, okay? So in other words, in a theoretical sense, we actually have the equation that can, if we can solve it exactly, we should be able to know any property with 100% accuracy, okay? Which is this equation here, right? Now, this equation looks deceptively simple, right? You look at it and you think, oh, it shouldn't be that difficult to solve, right? But it actually turns out that once you go beyond very simple systems like the hydrogen atom, solving this equation is actually very, very difficult, okay? So when we talk about quantum mechanics equations, simulations, we always have what is called the Tradeoff Trinity, okay? So there is accuracy, there's system size, and there's computational cost, okay? Or in other words, you can actually either get very accurate calculations, or you can simulate very large systems, or you will have to spend a lot of resources to do the calculations, okay? So this trade-off trinity just means that you, in most cases, you can actually only get two, or sometimes even just one of the things that you are after, okay? So ideally, we want to be able to simulate any size system that we wish. We want to be able to do it super accurately, and we want to be able to get the answer immediately, right? But unfortunately, the real world is not like that, okay? So you always have to decide what is the accuracy you need, what is the system size you can get away with. In other words, how do you choose your model system? And this is very important, right? How much computing power do you have, right? There are some things that, well, even if you have all the computing power in the world, you are not going to be able to simulate, right? All right. So when we start from the Schrödinger equation, okay, we can actually simplify it somewhat, okay, if the external potential has no time dependence, okay? And this is usually a useful approximation to make. And when the external potential, in other words, that V of RT over here, has no time dependence at all, what we can then do is that we can write the wave function, which is the solution to the Schrödinger equation, as a separable function. When we talk about separable function, it just means that instead of a function of both r and t, which is where r is the position of the atoms and t is time, okay, you can essentially treat it as a multiplication of two separate functions, one which is the function of just the position of the atoms, and another one which is just a function of time, okay? Now, once you do that, you can then decompose that the Schrödinger equation into two parts. One is the time-dependent part, and the time-dependent part, the solution is fairly simple. You just basically have f of t equals to this exponent over here. And what you are left with is basically you need to solve this stationary Schrödinger equation, which is just a function of your atomic positions of your atoms, okay? All right. Now, when we talk about a material essentially is just a collection of atoms, right? And a collection of atoms, you basically have your nucleus, which has some positive charge, and your electrons, which has a negative charge, okay? So when we think about the stationary Schrödinger equation for a collection of atoms, you can essentially write out all the terms that you need to consider when you are writing out the Hamiltonian of your system of atoms, right? And it is very intuitive, right? If you look at this equation, you can actually understand in a very high level what each of those terms mean, right? So first of all, you have your kinetic energy terms. One is, of course, the kinetic energy of your electrons, and another one is the kinetic energy of your nuclei, right? Okay, so we use ME is basically the mass of electrons, and MK is basically the masses of all your nuclei, okay? So, and this is basically the kinetic energy quantum mechanical operator, okay? Now, we know that electrons have a negative charge, and your nuclei have a positive charge, and of course, those will have electrostatic interactions with each other, right? So, between the nuclei and the electrons, you basically have an attractive force, okay, which gives you this term over here, which is you see this E square is basically the electron charge, and Z is basically your atomic number, which gives you the total Z times E gives you the total charge of your nuclei, and this Coulombic attraction between the nuclei and electrons gives you this negative term over here. You have electron-electron repulsion. In other words, your electrons tend to repulse each other. So this gives you this E square over the distance between the electrons over here. And finally, you have Coulombic repulsion between the nuclei itself. Sorry, this should be a positive sign here, but I will change it later, okay? And this gives you this final term over here, okay? So in other words, you already have, you can write out all the interaction terms that you need to think about when you are considering a collection of atoms, which is basically just nuclei and electrons, okay? Now, so to solve this equation, which is the stationary Schrödinger equation for a system of atoms, there are two broad approaches, and these two broad approaches actually shared a Nobel Prize between them for chemistry in 1998, okay? So one is by, one of the winners of the Nobel Prize is Walter Kohn, okay? So basically the father of density functional theory. And the other one is John Popo, who developed a lot of the computational methods we use in quantum chemistry approaches, okay? Now, what are the two approaches? Okay, so this is a very high-level overview of the two methods in which you can use to solve the Schrödinger equation, okay? One is called the variational approach. The other one is density functional theory. In the variational approach, basically what you do is that you expand the wave function as a linear combination of basis functions, okay? And in doing so, basically what you have is that you transform the stationary Schrödinger equation into a matrix eigenvalue problem, okay? So once you actually have that, you can then just solve the matrix eigenvalue problem and you get some solution to your Schrödinger equation. The good thing about the variational approach is that there is a clear path to more accurate answers, okay? So in other words, on a very theoretical sense, I know how to get more and more accurate answers for my quantum chemistry solutions to the Schrödinger equation, okay? If you say, well, I want a more accurate answer, I can tell you exactly how to go about getting the more accurate answer. But of course, within some cost limits, right? You basically do things like increase the number of basis functions or increase the number of cluster and configurations to account for electron correlation. And when you go to the infinite limit, you basically get the exact solution to your Schrödinger equation, okay? And this method is, of course, favored in quantum chemistry. All the chemists prefer this approach. Now, the second approach is called density functional theory. It is in principle exact. So when we actually get to the lecture on DFT, what you will see is that the first two theorems of Walter and Kohn on density function theory, they are exact. In other words, there were no approximations in the DFT equations itself, okay? However, in practice, the solution to the density functional theory equations, you actually have to introduce a lot of approximations to solve that, to solve those equations, okay? Unlike the variational approach, there is no clear path to more and more accurate answers, right? So yes, you can increase the size of your basis set, and you can increase the convergence criteria, but even if you max out those parameters, you are not guaranteed to be getting the most accurate answer possible, okay? Because this is primarily because of this part where you already introduce approximations in transforming the equation of density function theory into something that you can solve, okay? The upside is the computational cost is comparatively low for the same accuracy as the quantum chemistry approach. Usually the DFT technique is cheaper, and especially if you are working with condensed matter solids or so, that is usually the favored approach, okay? All right, now we will start with first with the some discussion of how you will actually go about solving the Schrödinger equation, okay? And in the next lecture, what I will go through is basically how do that then get into the quantum chemistry, the variational approach. Okay, so to solve the Schrödinger equation, in general, there are a complete set of eigenfunctions which we will denote with psi of I, and all these eigenfunctions have a corresponding eigenvalues E of I. Okay, so let us assume that the wave functions themselves are orthonormal. Orthonormal just means that if you do the inner product of each wave function, two wave functions, it will be a delta function. In other words, if you are doing the inner product of a wave function with itself, the value is 1. If you are doing an inner product of the wave function with another orthonormal wave function, essentially it will be 0. Okay. Now, if we based on this assumption, basically what we want is to basically look at this product of wave functions with the Hamiltonian. Okay, so we know that h of psi of j is just equals to the energy times the psi of j, because it is where the energy is basically one of the eigenfunctions. Okay, and you can see that basically this integral is just going to be equals to E times the delta ij. Okay. Now, with this, basically we can introduce what is called the variational principle. Okay. Now, the variational principle is actually a very simple concept. Okay. So let's define a gas wave function that is a linear combination of the real wave functions, right? So in other words, let us start with some gas of a wave function, which is phi over here, and this gas wave function is just basically a linear combination of my real wave functions, and that so C of I is basically the coefficients before every single wave function. Okay, and it is this summation, right? Now, if you go through the math, you can see that the integral of phi with itself is just equals to the summation of all the coefficients squared. Okay, and the integral of phi with the Hamiltonian with phi, okay, is just equals to summation of ci squared or E of I. Okay, where E of I is basically the eigenfunction, the eigenvalue for phi of I. Okay, now so let's define the lowest energy state, E of I, as the ground state. Okay, so when we solve the Schrödinger equation, most of the time we are interested in what is the lowest energy state of the system, okay, or rather the equilibrium state of the system. So we are going to do some very simple manipulation over here. So we can show that basically the integral of phi h and phi integral of phi h phi minus the ground state energy times integral of I squared is just equals to summation C of I squared E of I minus E naught. Okay. Now, if you look at this right hand side of the equation, what you will see is that C of I squared is of course always a positive number, and because we have said that the ground state energy is E of naught, any E of I is a value that is larger than 0. Okay, E of I minus E naught must be a value greater than 0. So in other words, this right hand side equation is always positive, right? Okay, so we basically what we then have is the left hand side is greater or equals to 0, and if you just manipulate this thing around, basically what you get is this equation over here. Okay, which basically say that if you have some gas wave function, it doesn't really matter how you construct the gas, okay, and you multiply, you do this integral of that gas wave function with h with phi h phi, divided by some normalization factor, which is just integral of phi squared itself. This ratio must be greater or equals to the ground state energy E of naught. Okay. So what this means is that we can always judge how good the gas wave function is by how low the energy is. Okay, so in other words, the lower the energy, the better is the gas for your wave function. Okay? So this is, in essence, is what is called the variational principle. In other words, whenever we are trying to solve the Schrödinger equation, we are essentially solving an energy minimization problem, right? We are trying to get to the lowest energy. We are changing the gas wave functions until we can get a gas that is as low in energy as we can possibly get. Okay, and that is the variational principle. Okay.